All right, so now we're moving on to box D here, derivatives of other exponential and logarithmic functions. So we're going to look at what you need to do or how this changes your rules when you're working with bases other than e for your exponential or your logarithmic function here. And we'll start by looking at the derivative of a logarithm to any base. So what we know is that from box C, we know that if we have y equals ln x, we know that the derivative is 1 over x. Now, how can we use this to help us find the derivative when we have y equals log to some base a of x? So let's just say if we have this as our function, how can we use what we already know to find the derivative? Well, what we can do is we can use the change of base formula for logarithms. Change of base formula, which tells us that if we have log to the base a of x, we can rewrite that as log of x over log of a. And for the base of our logarithm, we can choose whatever base we want, as long as the base that we choose in the numerator is the same as the base that we choose in the denominator. So what base would it make sense for us to choose here? You're saying 10? Not 10, because we want to use what we know already.
Oh, e.
We should choose e, because we know how to do derivatives to the base e. So this then becomes ln x over ln a. Now, in the denominator there, we've got ln of a. A is just the base of our logarithm, so it's just some number like 2 or 10 or 37 or whatever. So if we're taking the ln of some number, that's just another number. So this is a constant down here in our denominator. So if we want, we could write this as 1 over ln a times ln x, okay, where we've got a constant out front, and we've got our function is just ln x. So now if we take the derivative, well, it's just that constant, 1 over ln a times the derivative of ln x, which is 1 over x. Okay, so we can just rewrite this as, okay, derivative is going to be, what's the best way to do it? Just combine them together here, and we can just say it's 1 over x times the ln of a. Okay? So there's our derivative if y equals log to the base a of x. Okay, and there is our derivative rule. Okay? So if we're doing log to the base e, it's just 1 over x. If we're doing log to base something else, it's 1 over the ln, 1 over x, and 1 over the ln of a.
Why do we find a derivative of ln a?
Well, doesn't it just become like 1 over a, like,
And then switch places.
if I switch places, why isn't the derivative just a over x?
Yeah, why does it be over x?
Hold on a sec. And if instead of just having a straightforward logarithm, we've got a function that is log to the base a of some function of x, so we'll just write this as log to the base a of g to the x. We're going to apply the chain rule, and we'll get, instead of 1 over x, we will get 1 over g at x, again, times ln a, so the ln of the base, which is, again, just a constant. And then we've got to multiply that whole thing by g primed at x, or a derivative of that function, that inner function. So those are the two rules that you need to know for logarithm of some base other than base e. So let's take a look just at a couple of quick examples here. First one here is super simple. We got y equals log to the base 2 of x. So we're just going to apply that rule. The law exactly as it's written. So we've got log to the base 2, so we want 1 over x times the ln of the base, times ln 2. And that's all we had to do. Okay? If our base was 5, it would be 1 over x times the ln of 5. Speaking of base 5, that's what we have in the next question here. So the next question, we got y equals log to the base 5 of x cubed minus 2x squared plus 10. So this time we've got a composite function. So let's figure out what that inner function is here. So our inner function, g at x, is going to be x cubed minus 2x squared plus 10. And we know we're going to need the derivative of that. So let's take the derivative. We can do this term by term. So it's 3x squared minus 4x. Now we can go back and take the derivative of our entire function here. So following that chain rule, we're going to have 1 over that inner function. So that inner function is our g at x, so just x cubed minus 2x squared plus 10. And that has to get multiplied by the ln of our base. So we got base 5, so we need that factor of ln 5 appearing down in the denominator. And because we're doing chain rule, that whole mess gets multiplied by the derivative of that inner function. So we'll multiply this times, just in brackets over here, g primed, which is 3x squared minus 4x. Okay. And of course, we would straighten this up a little bit by doing 3x squared minus 4x over x cubed minus 2x squared plus 10 all times the ln of 5. Okay? And of course, we could factor the x out in the numerator if we wanted, if we needed to solve for something there. Okay? But that gets us our derivative. Okay. Are we ready to try the tough one here? Yeah. So we've got to do product rule because we've got two functions, x cubed and log to the base 2 of something. And then taking the derivative of this second term here, the log to the base 2 of all that stuff, is going to involve using the chain rule, not once, but twice. Because we have a function that is our logarithm function. Inside of that, we've got our square root function. And then inside of that, we've got another function, x squared plus 4. So let's see. We know we're using product rule. So we know our derivative is going to be, we've got to have a u, and we've got to have a v. V here is complicated enough that we might as well just use the derivative of v all by itself. So if v is log to the base 2 of this whole thing, let's just write that out. Log to the base 2 of x squared plus 4 to the 1/2. Well, now that I look at it, how can we simplify this from here using our laws of logarithms? Right. I didn't do this when I did this question with the previous class. Let's hope this works out the same. Okay, so now let's do our derivative here. So we're going to have that 1/2 is just going to stay out front. So we're going to have 1/2. To do our logarithm, we're going to have 1 over that inner function, which is x squared plus 4. Okay, that gets multiplied by the ln of the base, so ln 2. And then the whole thing gets multiplied by the derivative of that function that's inside the logarithm, so that 2x plus 4. So the derivative of 2x plus 4 is 2x. Okay. So then this 2 and this 2 cancel out. So we're left with x over x squared plus 4 times ln 2. So that just gets us v primed. So let's go back to our original function here and do our full derivative. So y primed is going to be u primed. So u is x cubed. So let's do 3x squared times v. Let's do log to the base 2 of, let's do x squared plus 4, again to the 1/2. We'll write it like that in case that helps us simplify things. And to this we have to add u, so x cubed, times v primed, x over x squared plus 4 times ln 2. And then let's look to see if anything can factor out of here. What can we factor out? Well, we've got x squared in the first term. We'll have x to the power of 4 in the second term when we do the x cubed times the x. So we can factor out x squared. Let's bring down the 1/2. So we'll have 3 over 2 log to the base 2 x squared plus 4 plus, if we factored out x squared, we're still going to have x squared left over here, x squared plus 4 times ln 2 down in our denominator. Can we simplify this any more? We could if we really wanted to. What we can
x squared plus 4 is -1. So you could just factor that out and get x squared plus 4 squared. That would, on the second term.
Could we?
Wait.
No, you can't, because those are inside the bracket, right? Like you're looking at this right here.